continue our discussions on planar kinetics of rigid bodies, and in this lecture I am going to take up a few more problems and show you applications of the equations of motion of translational and rotational dynamics for plane kinetics of rigid bodies. This is the first problem taken from the book of Merriam and Craig. It says a uniform 12 kg square panel is suspended from point C by two wires at A and B. If the wire at B suddenly breaks, calculate the tension T in the wire at A immediately after the break occurs. Now, when this wire at B breaks, at that instant, because the whole system was at rest initially and suddenly this break takes place. Therefore, we will consider that in the short time duration in which I am analyzing this problem and trying to find out the tension in the cable or wire AC, the plate has not gained any angular velocity. It has not started to move, it is still at rest. We consider this coordinate system, the tangent normal coordinate system, as I have shown here. There is something about this geometry that is given in the problem. These wires are at 45-degree angle to the edge of the plate, and because this is a square plate, the line join the line AG also makes 45-degree with that edge of the plate. Therefore, the net angle, the angle GAC is 90-degree. I have drawn this free body diagram. After the break takes place, it is the weight and the tension in the wire AC. We are going to write the equations of motion. Here I will not write down the translational dynamics equation, but I will show you that by writing the rotational dynamics equation about 2 points we can solve this problem, but this is because of this very special geometry. It helps, this geometry helps in the makes the equations very simple. I am going to write the rotational dynamics equation of the plate using this point A. Therefore, I need the acceleration of this point A. Acceleration of point A, because A is a point at the end of this wire CA, and therefore, C is a fixed point, and therefore, this point A, if it has to move, it will move in a circular path. Therefore, in this I have taken this tangent normal system aligned with that path. So, tangent ET cap is the direction in which A will move along that circle, and En is the normal direction towards the center of curvature. And you know the expression of acceleration in tangent normal system of a point. It is the tangential acceleration times ET cap plus v square by rho, radius of curvature of the path, times En cap. At the very beginning there is no velocity, it has not started to move, the wire has just broken and we are analyzing the problem. So, it has not gained velocity, therefore, velocity is 0, therefore, acceleration of point A at time equal t equal to 0 plus is just AT ET cap. Now, if I write the rotational dynamics equation about point A, then because of this angle there is a simplification, and that is what I want to indicate. Moment of inertia about A, this moment of inertia of the plate about A times angular acceleration plus this rho AG cross mass of the plate times acceleration of A is equal to the net moment of all forces about A. Here, because I have the acceleration of point A in the tangential direction, and tangential direction is exactly along AG, which means A has an acceleration towards the center of mass, and remember that this leads to a simplification, because rho AG and acceleration of A, these two vectors are co-oriented. These two vectors are co-oriented. they are in the same direction, therefore, cross product will vanish and therefore, this term drops out and I am left with a very simple equation I a times alpha is equals to m a. Let us now look at the expression of m a, which is straightforward. It is only the weight that produces moment about point A. Tension force is passing through A, so moment arm is 0. Therefore, we have only the weight producing the moment. I have written out this moment arm, which is A g in the coordinate system I have chosen. Also, the weight of the plate is represented in the coordinate system chosen. These things are very essential to note. Then it is straightforward algebra. I calculate alpha, the angular acceleration of the plate at t equal to 0 plus, just after the break occurs. Now, I use, because I have to calculate the tension in the string, I use the rotational dynamics about g, equation of rotational dynamics about g, and that is a very straightforward equation. You know, I g times alpha is moment about g of all forces, and here tension is the only force that produces moment about g. Substitute and you can solve for the tension in the string or the wire. If you plug in the values that are given in the problem, you will get tension as 20.8 Newton. So, that completes this problem. We move to the second problem. A uniform semicircular bar of mass m and radius r is hinged freely about a horizontal axis through A. If the bar is released from rest in the position shown where AB is horizontal, determine the initial angular acceleration alpha of the bar and the expression for the force exerted on the bar by the pin at A. Again, this problem is sourced from the book of Merriam and Craig. We consider again the plane polar coordinates, and I have taken the coordinate system aligned in a special way, so that E r is along this line A g. Remember, for a semicircular ring like this, the center of mass is at a distance of 2 r by pi from the center of the ring. I have aligned E r cap direction in the direction of A g. A is the hinge point, g is the center of mass, and E theta is taken in the direction of increasing theta. The free body diagram has the weight of the ring and the reaction forces. Again, the reaction forces at the hinge A I have resolved in the E r cap and E theta cap directions. I have these I can calculate these distances. Rho is this distance A g, and moment of inertia about A, which we will require in our calculations. Equation of motion, the translational dynamics will be for that I need only the acceleration of center of mass. If I write the E r cap equation is this, so mass times acceleration in the E r cap direction is equals to the net force in the E r cap direction. We have A r and a component of the weight. Similarly, in the E theta cap direction I have this equation. I am using the point A to write down the rotational dynamics equation, and that is why I have this moment of inertia about A, which turns out to be 2 times mass times radius square. Moment of inertia times angular acceleration must be equal to moment about A, which is mg rho cosine theta. We have the moment only because of the weight. The plan is to solve for we have to calculate the angular acceleration as soon as it is released, and then we will have to find out the forces at the hinge. From here I can solve for theta double dot, which is the angular acceleration, and that is what I have to find out at time t equal to 0 plus, that means just it is released. Sin theta is 2 r by pi rho. This can be found because I have this triangle. CGA, and it is a right angle triangle. I can write down sin theta, I can write down cosine theta, and right at the beginning t equal to 0 plus, when it is just released, it is at rest. So, theta dot is 0. I can solve for angular acceleration, turns out to be g by 2 r, and I can also solve for the reaction forces, because I know alpha. I have solved for alpha. Here I can substitute here to calculate a theta, and a r is very simple because theta dot is 0. This is 0 at t plus t equal to 0 plus. I can solve for a r and a theta. So, that completes this problem. So, I have used the rotational dynamics equation about A, I have used the translational dynamics equations which is for G, and I have solved these 3 unknowns, the reaction forces, 2 reaction forces, and the angular acceleration, 3 unknowns from 3 equations. We move to this problem of a ring. It is a split ring of radius r. Split ring is a ring with a gap here, as you can see. A split ring of radius r and mass per unit length rho is rotating with a constant speed omega. It is shown, the direction of omega is shown about a vertical axis which is perpendicular to the screen. It is a vertical axis through O and perpendicular to the screen. Using the differential element shown, it is already shown in the problem, in the figure, derive expressions of shear force N, again shown in the figure, ring tension T, and the bending moment M in terms of the angle theta. This force, which is perpendicular to the ring element, is the shear force, which is along the ring element is the tension, and bending moment is a force which tries to bend the element. We have to solve for these forces as a function of theta, and you should notice how theta is being measured from this dashed line. Coordinate system, plane polar coordinates is the only choice. There is a prismatic body, so we can use the equations of motion for planar kinetics. The free body diagram of that little element is already shown. Because these forces are varying with theta, therefore, I have shear force on the face at theta as N, and at the face of theta plus d theta I have the shear force N plus d n, it is varying with theta. Similarly, for the tension on the face at theta it is T, at theta plus d theta it is T plus dt, and same way for the bending moment. Equations of motion of this element. Now, acceleration of that element, this element is small enough, location of the element it coincides with the center of mass, it is an infinitesimal element. Acceleration of this element in plane polar coordinates, the only term that remains is the centripetal acceleration, because its radial coordinate is not changing, and it does not have any radial velocity, therefore, no Coriolis term, no Coriolis acceleration, no radial acceleration, it is no tangential acceleration, because it's the ring is rotating at a constant angular velocity. Therefore, the only acceleration that we have is the centripetal acceleration minus r omega square E r cap. Now, I am going to write down this equation of motion for this element. It's a like a point particle. Here what we have is rho is the mass per unit length of the ring. rho times, and r d theta is the little length of that element. Therefore, this gives us the mass of the element. Mass of the element times acceleration is equal to the net force on the element. What we have is the shear force, which is shown here at theta plus d theta, which is n plus dn. This has an inclination with the radial direction. You will notice that because of this extent d theta, or the length of angular extent d theta, or the length r d theta, there is an inclination of that cut face. Therefore, this shear force will have a component in the ER cap direction, which is d theta by 2, and cosine d theta by 2 will measure that component. Therefore, n plus dn cosine d theta by 2 is the component of n plus dn in r cap direction. Similarly, on the theta face where the shear force is n, we have it in the direction of negative ER. Therefore, this negative sign comes, and we have again cosine d theta by 2 as the component. The tension also makes an angle with the ER cap direction, because this angle this is along E theta direction, E theta cap direction, and this tension makes this angle d theta by 2 with E theta cap direction. Therefore, on the ER cap direction we have t plus dt sine d theta by 2 in the negative direction. Same thing happens for t, that means on the face at angle theta. All these are components of the force in the ER direction, ER cap direction. Next, we write down the components of forces in the E theta cap direction. T plus dt, this will now have a cosine d theta by 2 component. T will have cosine d theta by 2 component in the negative E theta direction. N plus dn and n both have sine d theta by 2 component in the E theta direction. That completes the equation of motion for the translational dynamics. Now, from here if you look at the components, if you look at the two directions, this is the E r cap direction. From the left hand side we have this expression of mass times acceleration. So, rho r d theta, rho r square d theta omega square, and here I have made some simplifications. What I have done is cosine d theta by 2 I have approximated as 1, and sine d theta by 2 I have approximated as d theta by 2, and I also have dropped the second order small terms, and I have done I have taken this d theta from the left hand side to the right hand side, and that is how I get d and d theta, etc. Now, then what we have is this is the equation of translational dynamics in the ER cap direction. In the E theta cap direction, on the left hand side we do not have any acceleration in the E theta cap direction, because there is no tangential acceleration, no Coriolis, etc. And from the right hand side we get dt d theta plus n equal to 0. Rotational dynamics equation, this element is a very small element and its angular acceleration is 0. Why its angular acceleration is 0? Because the ring is rotating at a constant angular velocity. Therefore, its angular acceleration is 0, and therefore, moment of inertia of this element times angular acceleration is 0, therefore, 0 is equal to sum of all moments about the center of mass, and in that we have the bending moment and the shear force producing first order terms, small terms. If I simplify this equation, I get d m d theta plus n times r is equal to 0. Now, I have these three equations, these three first order ordinary differential equations to solve for, to determine n, t and m. Since when we integrate we will have constants of integration, therefore, we need to uniquely solve for the system, we need boundary conditions, and boundary conditions are provided by this split end at this split. Here the shear force is 0, the ring tension is 0, the bending moment is 0. Therefore, I must have the shear force at theta equal to pi is 0, the tension at pi is 0, the bending moment at pi is 0. I start integrating, but I first simplify this using these two equations 1 and 2. I eliminate t. So, what I do is from here I eliminate t in the and I get an equation for d and d theta. If I just derivate this with respect to theta, the left hand side is not a function of theta. Therefore, second derivative of n with respect to theta minus dt d theta, which is again minus n. So, I get plus n equal to 0. Therefore, now I have a second order ordinary differential equation in n whose general solution is in terms of trigonometric functions sine and cosine with two constants of integration C 1 and C 2. Using this boundary condition that the normal the shear force at theta equal to pi must vanish, I can drop the C 1 term, because at theta equal to pi cosine pi, which is minus 1, will start contributing, whereas sin pi will go to 0. Therefore, I can have only this C 2 sin theta term. This satisfies this condition that the shear force at pi is 0. So, I have not been able to as yet solve for C 2. Let us look at the tension solution. Now, if I have n, if I get n from here, I have n in terms of C 2, I just substitute in the first equation and solve for the tension. Therefore, tension becomes C 2 times cosine theta plus rho r square omega square rho r, and what I get out of this when I use the condition that the tension at theta equal to pi is 0, we can solve for C 2. Therefore, from this boundary condition on the tension, I can now get complete solution for the unique solution for the shear force, which is rho r omega square sin theta. And also, since C 2 is now known, I already have the variation of the ring tension, and the bending moment is obtained from the third equation by integrating the third equation, straightforward integration. I have this expression for the bending moment, and I use this condition when I integrate. I have a constant of integration which is solved from this condition that the bending moment at pi is equal to 0. So, this completes this ring problem. Let me just summarize. We have looked at some problems to show the application of these equations of translational and rotational dynamics for planar kinetics of rigid bodies. With that, I will close this lecture.